Right. So, okay. So basically, with this question, they want to make it so there's no tension in the rope whilst everything is all fine. So that it's a wooden box full of usually is in a sling hanging on. The weight of the sling is negligible. Okay, wait. The catapult is designed so that the weight of the beam and the weight of the empty wooden box has no effect on the tension of the rope. Right. How do they achieve this? Well, the way they achieve it, first of all, as you can see, the center of the mass of the beam um, is at the pivot. Okay, and the reason for that is because another thing that they've done as well is that so the center of the mass of the beam and the box, of course, is at the pivot. Because as you can see, the center of the beam is the center of the mass of the beam is going to be shifted over to the left. But the the anti-clockwise moment caused by the very light empty sling and the mass of the beam, that moment that's going to be causing an anti-clockwise moment, that's going to be equal to the clockwise moment caused by the counterweight. So the counterweight is trying to get it to rotate clockwise, but the weight of the beam and this sling is trying to make it rotate anti-clockwise. And so they've set it so as the moments are equal to each other, and therefore this rope here will not be under tension. So that's really this is an equilibrium problem, okay, but specifically around moments. Now, what it says then is the stones in the counterweight have a total mass of 610 kilograms, and the projectile weighs 250 newtons. So now they've changed the situation. They've added stuff to the counterweight. They may have added stuff to the counterweight, and they've added something to the projectile. So calculate the tension of the rope. So this is a little bit tricky, but the basic. Let me just get what I'm going to do. I'm just going to get the mark scheme up so you can see how they've done it. Something just had a pop up appearing, so I can't. Try that again now. Yeah. Remember, at the moment, it's in equilibrium, but as in there's no rotation, but that's because the tension of the rope. So the first thing we're going to realize is that so the anti-clockwise moments is going to be equal to the clockwise moments. Now the clockwise moment is going to be 1.5, so that's the distance, multiplied by so that the stones in the counterweight is a total mass of 610, multiplied 610 multiplied by the strength of gravity. And let's just see what they've done here. So 9.81 times 1.5. Yeah, so that's going to be equal to 8,976 Newton meters. And that must be what the bit on the left is also equal, the anti-clockwise moments. Now, the anti-clockwise moment is one of the things we will need to take into account is this angle here. So we'll look at that in a moment. You may not have considered that originally. Now, the anti-clockwise moment is going to be so the stones in the counterweight have and the projectile weight. So they've just tried to catch you out here because they've given you the mass on the one side, but the weight on the other one, which is a bit sneaky. But so in the right, and the one on the right hand side, we need to multiply it by the strength of gravity. But on the left hand side, we don't need to do that. So okay. All right, I'm going to carry on going with this. It looks like you've lost the Zoom call, but you'll get the video afterwards anyway. So 250 multiplied by 4 plus, and then I'm going to just say for now we're just going to say the moment caused by the tension in the rope. So by rearranging that, we can see the moment caused by the tension in the rope is going to be equal to 8,976 minus this 250 multiplied by 4, which obviously is going to be 1,000. And that's all in Newton meters. So let's work that out first. Okay, so that's easy, isn't it? It's just going to be 7,976 Newton meters. Okay, now this is when the angle is going to come in. The point is, it's got to be the component of the tension that is perpendicular to the distance from the pivot. So what component of this tension is vertical, essentially? So if we draw a triangle here, we've got the hypotenuse is what the tension is. And this would be the vertical component of the tension down here, or TV. And this is 50 degrees like that. So it's going to be SOHCAHTOA, so sinus equals the opposite over hypotenuse. So TV is going to be equal to T sine theta. T sine 50 in this case. And so it's the vertical component, which we would then multiply by the distance from the pivot, which is also 4 meters. So what this comes down to then is, when running out of space here, so I'm just going to move a few things around. Well, we know that this is the moment caused by the tension is that, and the force due to that moment, the vertical component of the force due to that motion is going to be this. So therefore we can say that the moment due to the tension is going to be equal to the distance multiplied by the vertical component of the force. So 4 is the distance, and the vertical component is T sine 50, and that's equal to 7,976 Newton meters. So now we've got a reasonably simple equation which we can rearrange to find out what the tension is. So the tension is going to be 7,976 Newton meters divided by 4 sine 50. Looks like I've done it slightly differently to what they've done there. So let's hopefully we're going to still get 2,600. And we do. So it actually ends up being 2,603, rounding up, Newton. So that's it. So I'm going to just send this over to your mum, and she can send it to you. All right. Cheers. Bye.